All right. So our next thing we're doing already is participating in our electrical competition in December. I wish we could start that. Let's do that. So everyone, please welcome Mikaela.
Hi, everyone. My name is Mikaela Meyer, and I'm a senior data scientist at the Miter Corporation. The Miter Corporation, much like IDA, also operates federally funded research and development centers. Today, I'm going to be talking to you about a project that I worked on with my colleague, Zach Turner at Miter, as well as some folks from the United States Census Bureau and Tumult Labs on slowly scaling per record differential privacy. In general, many groups that collect data might want to make their data public. Perhaps they want researchers to be able to use the data, or they just want to be transparent with members of the public. In the case of the United States Census Bureau, the agency produces many data tables that are important for many of our research. However, they also have an obligation to protect respondents' privacy, and many other groups are interested in data privacy as well. However, it's also important to make sure that your data is still usable or representative of reality. So therefore, it's important to privatize data in a way that doesn't change the values of the data so drastically that the data set is no longer usable or no longer representative of the truth. It's a delicate balance, especially depending on the nature of your data set, which we're going to talk about now. So to make this a little more concrete, imagine this scenario where we have two data sets of businesses, and the only difference between data set D and data set D prime is one row, this ID number 2. And so let's say that I'm an attacker and I want to know if business ID number 2 is in the data set that I'm looking at. The attacker might query then the data set. For example, I might be looking at then the median average salary. And then I'm going to look at this median average salary query and try to determine, based on what I know about ID number 2, that they may or may not be present in this data set. And doing so might allow me to make this correct inference. So the broad goal of differential privacy is basically to prevent this by adding noise to queries to bound the probability that an attacker can tell whether they are querying D or D prime. Ideally, of course, this probability is low. And in general, this basically means I'm trying to make sure that someone can't tell whether ID number 2 is in my data set. So if an attacker cannot tell whether they are querying D or D prime, we can say this mathematically, that basically the distance between the two outputs from applying mechanism M to D and D prime is bounded by this rho of alpha from above. So rho in this case represents the privacy loss, and it's a constant across all of the entries in your data set. This is important for what we're going to be discussing later. And so we want to inhibit the attacker's inferences by ensuring that the difference basically between M of D and M of D prime is acceptably small. M also in this case refers to our differential privacy mechanism, which I will also explain later. So the motivation for our work is that with traditional differential privacy, if you have a data set with a few large outliers, such as one that could be explained by this box plot here, you then have to add noise on the scale of the largest outliers to mask their presence. And this can then harm the utility of your data set that you're trying to release. One example of such a data set could be data about business sizes. So you can think about, say, a county that is perhaps smaller, and maybe there's a Walmart in this county, but then there's also a number of small businesses. And what you're trying to do is you're trying to protect the data privacy, not only of the small businesses, but also of Walmart. And you're trying to then also keep the utility of your data set fairly high. So Census wants to protect privacy in these cases. Census also collects business data beyond the individual respondent census data. And so that was the motivation behind our project. So we propose slowly scaling per record differential privacy to better handle these data sets with large outliers. So in this case, rather than giving all observations in the data set the same amount of protection, we can protect some records, i.e. smaller records, more strongly than others by allowing the upper bound to vary with the record's value. So as we were looking at earlier, we saw that this distance metric was bounded up from above by rho of alpha. And now what we're saying is that we're going to let, instead of rho be the constant that's multiplied by alpha to determine this upper bound, we're using this record-specific policy function, P of R. And so P of R is record specific, like I was saying. And when we think of a record, that basically just means a row in your data set. So when we were looking earlier, ID number 2 would then have a different upper bound than ID 1 or 3. And so we can then therefore add noise that scales with the size of the record or add noise from fat tail distributions to better allow for the slowly scaling per record differential privacy. So as your record value is increasing, this upper bound is also going to be increasing. Our mechanisms that we propose fall into 2 categories, additive and transformation. For the additive mechanisms, what we're basically doing is we're adding noise from distributions with thicker tails than the Gaussian or normal distribution. And for our purposes, we derive properties of 2 distributions, the generalized Gaussian and the exponential polylog. We should note that in our paper, we're not the first to derive the variance of the generalized Gaussian distribution, though we were the first to do so for the exponential polylog distribution. In terms of the transformation mechanisms, what we're basically doing is we're taking our query result Q of D, so that median of a column, through a transformation function f. Think the square root function, the natural log function, something like that. And then we add Gaussian noise to that transformed value, and then we invert the transformation function with inverse function g, and that is our noisy output. So in terms of the mechanisms that are considered in this paper, I show in the top table the transformation mechanisms that we considered, and in the bottom table, the additive mechanisms. There's a lot of math on this slide, but really the takeaways here are that for the variance formulas for the transformation mechanisms, the variance of the transformation mechanism scales with the query value. So we see that in all of these formulas, Q of D is part of the formula for the variance, and so therefore, as your query is increasing, your variance is also going to be increasing. This is not true of the additive mechanisms, where we do not see Q of D present in these formulas. It's also worthwhile to note that this identity mechanism that we're talking about in the top row is not a slowly scaling per record differential privacy mechanism. This is basically going to be our baseline when we're comparing these mechanisms later on and their performance. F of x in the transformation mechanism table is the transformation function that you're applying to your query. So like we were talking about earlier, this could be the square root, some kth root, or the log function. And then for the additive mechanisms, what you should be thinking of is that you're sampling noise from some distribution that has a density function of the e to the f of z. So this f of z column then is what you're exponentiating. And this last column here for both of these tables gives our policy functions, our P of R that we were looking at in those upper bounds on the previous slide. So this is what is allowing us to scale this upper bound with our record value. So our mechanisms guarantee less privacy loss when your data set has large outliers. And so what we're showing on this slide is basically an instance where we chose parameters for our mechanisms such that the variance was constant across all of the mechanisms. And on the y-axis, I'm plotting the privacy loss, and on the x-axis, I'm plotting a query value. And each of these different colored lines represents our different mechanisms. And if you recall, the Gaussian mechanism is not a slowly scaling per record differential privacy mechanism. So this is what we're comparing ourselves to. And what we see is that for smaller values, for smaller query values, the Gaussian mechanism actually guarantees less privacy loss than our slowly scaling mechanisms. And so in these cases, it actually might not be beneficial to be using our slowly scaling mechanisms if you only have smaller query values. However, we see that as the query value increases, the Gaussian mechanism is incurring more and more privacy loss, whereas our slowly scaling mechanisms have now started to degrade in terms of the amount of privacy loss that they're incurring. And so we therefore see that if you have larger query values in your data set, so larger outliers, our slowly scaling mechanisms are going to incur less privacy loss for each of these records. And that's when these mechanisms are most beneficial to use. So to better understand how our mechanisms perform on a real data set, we empirically evaluate our mechanisms using 2 different data sets that both have properties that mimic what we would expect from a data set that has large outliers, and therefore a data set that's good for our mechanisms to be used on. So for one of the data sets, we use the USDA's 2019 cattle inventory survey. This is a data set that is publicly available, which is great. And then we also use simulated county business patterns data from the Census Bureau. This is unfortunately not publicly available. But in terms of the queries that we're interested in for each of these data sets, we are interested in the number of cattle in each state for the cattle inventory survey. And then for the county business patterns data, we're interested in queries such as the number of employees at each business, the total annual pay, and the total Q1 pay for each county and industry. For our experiments, we used a Python package that was developed by Tumult Labs to implement all of these mechanisms. And then we made all of our plots in ggplot, and I just wanted to give a shout out to the Wes Anderson package, which gave us the colors for our palettes. When I was in grad school, I was bored one day and really wanted to jazz up my plots, and I found the Wes Anderson package, which I thought was kind of fun as a movie fan. So first, we're going to look at some cumulative distribution functions, or CDFs, which showed that our mechanisms incur less privacy loss. And so on the y-axis here, I'm plotting the proportion of records in our data set that have a privacy loss that is less than or equal to a respective value on the x-axis. So for example, if we're looking at this middle line here on this left plot, that x value is 50. And so any points that are then on this x equals 50 line represent the proportion of records for that mechanism that have a privacy loss that is less than or equal to 50. So as a result of that, our goal for these plots is to see that we basically have fast growth. We want these points to reach 1 as quickly as possible because that means that we have lower privacy losses for all of our records. And so each of these points are colored by the mechanism that they represent. On the left-hand side, we have the transformation mechanisms, and on the right-hand side, we have the additive mechanisms. I should also note that for the purposes of our results, we're only focusing on the simulated county business patterns data set just because of time constraints. So we're trying to compare ourselves to the identity mechanism and the Gaussian mechanism. The Gaussian mechanism is the gold points, and the identity mechanism are these navy points. And what we find is that, again, at the beginning, perhaps, the Gaussian and identity mechanisms have lower privacy losses. So for smaller records, the Gaussian and identity mechanisms do great. But we then find that these points never actually hit 1. So there are records in our data set that have a privacy loss that is greater than 100 or greater than 30, depending on which one you're looking at. It's also worthwhile to note these differences on the x-axis. So actually, our additive mechanisms have much lower privacy loss than our transformation mechanisms based on the scale of this x-axis. And so we basically are finding that our slowly scaling per record differential privacy mechanisms are guaranteeing you low privacy losses even for large records in your data set. Next, we're going to think about the utility that we're still having in our data set based on how much noise we're adding to it. And so some of our mechanisms, unfortunately, incur too much relative error such that we maybe wouldn't recommend using them in these cases. And when we're talking about absolute relative error, I've put the formula on this slide, but basically you're looking at the absolute difference between the noisy count that you're obtaining from the differential privacy mechanism to the true count that you originally had in your data set, and you're comparing this difference to what the true count really was. So the blue lines on each of these plots represent 100% absolute relative error. This is basically really bad. You would be effectively doubling the size of the records that you're calculating. The orange lines you can think of representing a line of tolerance, if you will. So this orange line represents where you have 10% absolute relative error. And you can think of basically setting this line such that anything that occurs below this line is tolerable and anything that occurs above this line is not really great. So in particular, what we see is that for our fourth root and log mechanisms over on the right-hand side, that all of those box plots pretty much are located between the blue and orange lines. And so that means that for both of these mechanisms, the relative error that we're incurring by using them is really not tolerable. We should not be excited to then release these statistics out into the world because it's really harming our data utility. However, we do see that for the generalized Gaussian and exponential polylog mechanisms, that these box plots are not necessarily always below the orange line, but they're doing still better than at least the fourth root and the log mechanisms. And again, we're also comparing ourselves to the Gaussian and identity mechanisms, which we also see don't always occur below the orange line. I should have also said this earlier, but what we're doing on the x-axis is we're binning by quintile of the true sum. So we took our true query values, we binned them into 5 different categories in ascending order, and so that's how we're plotting this on the x-axis. And so we're seeing this decreasing trend, which basically means that our absolute relative error for the largest sums is less than the absolute relative error for our smallest query values, which is great because typically under traditional differential privacy, we're not able to guarantee that large records have a good privacy loss value. So in conclusion, we developed formally private mechanisms with slowly scaling privacy loss to better handle positively skewed distributions or distributions and data sets with large outliers. For the additive mechanisms, what we're doing is we're adding noise from fat-tailed distributions, which therefore lets privacy loss scale slowly. And for the transformation mechanisms, our privacy loss scales slowly by transforming the query, adding noise, and then inverting the transformation. We did see, though, that in our experiments, neither type of mechanism uniformly dominates. And so further work is therefore needed to determine the conditions for choosing a specific mechanism and policy function. And again, our mechanisms aren't necessarily beneficial to use in all use cases. This is really the most useful if you have a lot of large outliers in your data sets that you're trying to protect. So our paper is actually posted on arXiv. If you scan this QR code, that will take you to our arXiv paper. And if you have any questions after this talk, feel free to find me. You can also email me. My email address is there, as well as my website. And then you can also email our corresponding author from the Census Bureau, Dr. Brian Finley. His email address is also present on this slide. Thank you so much. I really enjoy being at this conference, and I'm looking forward to meeting you all.